Okay, we're going to go through our second section about vectors in Chapter 6 here. This is section 6.2, titled The Dot Product of Vectors. And we're going to see how that ties into our problems with work and force. It says vectors can be multiplied in two different ways. One is called the cross product, or the vector product, or the outer product. That results in a vector that is perpendicular to the plane of the two vectors that are being multiplied. That's not really something that we're going to deal much with in this chapter. It says we'll explore this further in another chapter, but I don't think we're going to get to that in Honors Math 4. What we are going to focus on is what's called the dot product, or the scalar product, or the inner product. And that's going to result in a scalar, or just a number. So it says, recall that it is often useful to use arrows to name the vectors which they represent. So I'm just kind of going through some of the things that we learned in the last section here, talking about things like the different notations here. For example, we have where do we have it? Right here. I'll just use this. This is what's called our component notation. And then we have the linear combination notation. Oh, there it is right there, component form. And then the linear combination. A in this form, in either form, is the horizontal component, and B is the vertical component. All right, here's the definition of the dot product. The dot product is simply found by multiplying the two horizontal components together. So if you have vector u and vector v, we'd be multiplying the two a values together, and then we would add that to the two vertical components, so in this case u2 and v2. So we'd find the product of the horizontal, the product of the vertical, and we would sum them together. We have some properties of the dot product. It is commutative. The dot product of a vector with itself is simply the magnitude squared. The dot product between the zero vector and any vector is simply 0. And then we have the distribution property here, and being able to multiply a scalar c and u is the same thing as being able to multiply that scalar to a separate vector v and then find the dot product. All right, we are going to do a few examples here where we are finding the dot product. It's a pretty simple process. Again, we find the horizontal components product. We find the vertical components product. Oop, getting ahead of myself there. And we add those together. So we have 15 plus 8, which is 23. So notice how the dot product results in just a number. Now we have 1 times -4 plus -2 times 3. So we have -10. Now we have the component form. We're going to be finding linear combination form. We'll be finding a dot product the same way. Multiply your horizontal components. Our vertical component in that first vector is -1. Vertical component in the second vector is -5. So we have 6 plus 5, which is 11. So there's 3 examples of finding the dot product between two vectors. Dot product can be used to find length or magnitude. And it goes through this little process right here. Basically, what you're saying is just giving another way to find magnitude using the a squared plus b squared method that we used in the last section. So what I just wrote here is we're just going to use that technique from 5.1, basically that the magnitude of u is the square root of a squared plus b squared, where a and b are the vertical and horizontal components. So just how we have been finding magnitude, we're just going to stick with that. But you can use the idea of squaring a vector in order to find its magnitude. All right, this is going to be a useful theorem for us finding the angle between two vectors where one of them is not a horizontal or a vertical vector, so it might not be easy to find out what the angle between them is. So here's what we're going to be using. The fact that the cosine of theta is equal to the dot product over the product of the magnitudes. So it's the ratio of the dot product between the two vectors and the product of the magnitudes of the two vectors. So since that's what the cosine equals, then theta would equal the inverse cosine. I think it is important that we just note what these two things represent. So that's the dot product, and the denominator is the product of magnitudes, just to break down what this ratio actually is. Magnitudes. So here we have two examples. It says use an algebraic method to find the angle between the vectors u and v. U is 2, 3, v is negative 2, 5. And they actually have that picture right there, so we're looking for that angle theta right there. Well, we know that we need to find the magnitude of both of these. So the magnitude of u is going to be the square root of 4 plus 9, which is the square root of 13. The magnitude of v is going to be equal to the square root of, the square root of negative 2 squared and plus 5 squared, so the square root of 29. And we're also going to need to find the dot product between these two vectors. Dot product between these two would be 2 times negative 2 plus 3 times 5, which is negative 11. So we have all three pieces that we need here. We know that theta is going to be equal to the inverse cosine of, and then just going off what we had up here, the dot product, which we found to be negative 11. Actually, it's positive 11, isn't it? And that's a huge deal right there. If I would have accidentally put in negative 11, what that would have resulted in is a negative value inside my, trying to write and talk at the same time, a negative value inside of this inverse cosine. If you remember, a negative value inside the inverse cosine would give us an obtuse angle, and clearly that is not an obtuse angle, so hopefully we would have caught that at some point in time. I'm sure you caught it right away. So we're just going to type that into our graph calculator. Be careful with the division, making sure that you keep that product down in the denominator. So we've got the inverse cosine. Just make sure that I'm in degrees here. The inverse cosine of 11 over the square root of 13 times the square root of 29. We can just put those into one, because of our properties of radical multiplication, we can just do 13 times 29 within one radical. And we're going to end up with 55.49, about 55.5 degrees. All right, our next one, we have a magnitude of, and here's a picture of our next problem. We have a magnitude for u of the square root of 5, 4 plus 1, and a magnitude of v, the square root of 10, 1 plus 9. And the dot product between those two is going to be negative 2 plus negative 3, which is negative 5. So theta is going to be equal to the inverse cosine of the dot product, okay, this time it is supposed to be negative, over the product of those magnitudes. So we have the square root of 5 times the square root of 10, which we know is going to be the square root of 50. Let me just write here that those magnitudes multiplied together, I know is going to be the square root of 50, because I know I can simplify that. That's going to be 25 times 2, so 5 square roots of 2. And the reason why I did that is because, hopefully you notice here, this can be simplified, and not only can it be simplified by canceling those out, you have 1 over the square root of 2, or negative 1 over the square root of 2, which which rationalizes to the square root of 2 over 2. So we're taking the inverse cosine of negative square root of 2 over 2. So this is why it says use a calculator to approximate the exact answer when appropriate. It's not appropriate here to use a calculator because we know that the inverse cosine of negative square root of 2 over 2, since it's negative, it's going to be an obtuse angle, and cosine, the angle that has a cosine value of the square root of 2 is obviously 45 degrees, but we want to use that as a reference angle. Get this out of the way here. As a reference angle in the second quadrant. So if we use it as a reference angle, the angle that we have here is 135 degrees. And that's what theta is. Inverse cosine of negative square root of 2 over 2 is 135 degrees. So that is our angle between those two there, and it looks like a pretty legit answer. Okay, the next thing we're going to talk about here are orthogonal vectors and perpendicular vectors, and then also parallel, although it's not talked about there. Orthogonal vectors, actually we'll describe our first bullet point here. It says if vectors u and v are perpendicular, that is if the angle between them is 90 degrees, then the dot product between them is equal to the magnitudes multiplied together times the cosine of 90, which is 0. Now, orthogonal says the same thing. If the dot product between two vectors is 0, then it's orthogonal. So what does orthogonal mean? Well, the terms perpendicular and orthogonal really are the same thing, except in terms of the 0 vector. It says the 0 vector has no direction, so it really cannot be perpendicular to any vector. So what we use instead is the word orthogonal. But when you're saying orthogonal, basically what you're saying is that two angles are perpendicular. Okay, except in the case of the 0 vector, you can't say that it's perpendicular with anything, so we use the term orthogonal. So what we're basically going to be looking for here, in fact, I'm going to write this right here, basically, two vectors, are orthogonal if their dot product is 0. And orthogonal, again, for all intents and purposes for us means that they are perpendicular. So there's an angle of 90 degrees between them. The other thing we're going to talk about is these vectors being parallel. Well, parallel vectors would have the same direction, but possibly different magnitudes. So really, if one is a constant multiple or a scalar multiple of the other, then they are parallel. So if I could take one vector and multiply it by a constant and get the other vector, they're parallel. So let me just give you an example of two parallel vectors. Would be something like 2, -5, and 1, -5 halves. Those are two parallel vectors, because I know that I can get from this one to this one simply by multiplying it by a scalar of -5. Therefore, these are, multiplied by a scalar of 1/2. Therefore, these are parallel vectors. All right. Another parallel vector with those, I can multiply this guy by anything and keep getting parallel vectors. 4, -10, that's a parallel vector. All right. So that is the definition of two parallel vectors, is that one is a scalar multiple of the other. So example 4 says, prove that these two vectors, 2, 3, and -6, 4, are orthogonal. We want to prove that they are orthogonal, so we need to show that their dot product is 0. So this is a pretty straightforward problem here. We just need to prove that the dot product between them is 0. So let's find that dot product here. We have 2 times -6, plus 3 times 4. So they are orthogonal. I'll just check they're orthogonal. I'm going to throw another example here about this same concept. This is actually a little bit more what your homework is going to be like. Call it example 4B. Here's the type of question you'll be asked. Are u, and I'll give u in component form here. Let's make it 2, -7, and V, negative 414, orthogonal, parallel, or neither? Well, the first thing I would check before I start looking at the dot product is one a scalar multiple of the other? Well, as we look at this one, if I take 2 times that 2 negative 7, I would get 4 negative 14, which isn't what we want, but hopefully you recognize that it's pretty close. If we were to take negative 2 times it, and your scalars can be negative, then you would get negative 414. So I'm going to say since negative 2 times u gives us v, they are parallel. One is a scalar multiple of the other. Okay, if they aren't parallel, if one is not the scalar multiple of the other, then the next thing I would do is say, okay, if it's not parallel, I would check to see if they're orthogonal by finding the dot product. If the dot product is 0, they're orthogonal. If neither of those things are true, then the answer is just neither. Okay, but in this case, it ends up that they are parallel. All right, we're going to stop this video here, and we'll have a second video for the rest of this section coming up.